Hi, everyone. So today we'll discuss counting. So that will be last lecture on counting. All right. So, but counting, we are going to discuss today are much more complicated. It involves repetitions when we can count some objects more than once. So that will cause a lot of trouble, actually. In fact, counting is a very difficult problem. When repetition is not allowed, we have a permutation or combination. They are relatively simple, but when repetition are allowed, it's getting very, very complicated. It's very, very difficult. Okay. So in terms of repetition, usually we will use so-called box and the ball box model. We have some number of boxes and some number of objects. Usually we call them balls. Okay. So what we want to do is all these boxes. I will give you a connection between this repetition thing in a minute. Okay. So we want to put all inside the boxes, and we want to count number of different ways. Typically, the problem can be divided into 4 situations, regardless based on whether the boxes are different and the objects are different. So there are 4 situations, depend on if they are different or not. Okay. So when we say the boxes are different, then there are 2 situations depending on whether balls are different or not. So there are 2 situations when boxes are different. And when boxes are not different, we cannot distinguish one box from other. So boxes are not matter. What matters a number of objects inside boxes or which object is inside box. So that's what we mean by indistinguishable boxes. These boxes will be recorded the same. So we don't have the labels. So that's this situation when boxes are indistinguishable. All right. Now again, we have 2 different situations, depends on whether balls are different and all the same. Both situations are very, very difficult. We don't have closed formula for these 2 situations at all. When balls are different, it has something to do with second of kind Stirling number. It's a complicated number. In the second case, it's related to so-called partition problem. Both are very difficult. So we're not going to discuss for this course. So we can ignore this part. It's too difficult. Very much involved. Okay. So erase them. So today we'll just focus on this case when objects are distinguishable. Actually, when boxes are distinguishable, so we do have names for boxes. Say 1, 2, 3. Then there are 2 situations, depending on whether these balls are different balls or same ball. We cannot tell from one from the other. So that's indistinguishable. There are 2 different cases. Trying to make music, it sounds a little bit loud. Okay. All right. So let's see. So let's say maybe consider the first case first. When balls are different. So when balls are labeled as A, B, C, D. So let's look at this particular situation. So I give you 3 boxes labeled by 1, 2, 3, and I have 4 balls A, B, C, D. So we can regard these 4 balls as different colors. So maybe red, black, blue, yellow. Maybe I can tell one ball from another. So in this case, all are different. So we're considering this one. But how many different ways can we put these 4 balls into these 3 boxes? All right. So in this case, it's quite simple. It's really just a permutation. Because for the first ball, there are 3 different ways. So for this ball A, there are 3 different situations. We can put ball A in box 1. So we have 3 boxes labeled by 1, 2, 3. So A has 3 different choices. Or we put it here, or we put it here. Each will give a different situation. So that's really, we have 3 choices for A. Similarly for B, there are 3 different choices. I can put B here, or here, or here. So each will give a different situation. So for example, if that's the case, so that will be one result by putting AB. All right. So by multiplication rule, multiplication rule, it will be 3 times 3. All right. So similar for C and similar for D. So that's actually we know how to do it already. So if there are n boxes, k objects, it will be just n raised to power to k. So which we know how to do it by using a multiplication rule. All right. Now the situation is a little bit different. Each box will have a capacity. You cannot put everything inside the box. Maybe actually not only capacity, each box requires a fixed number of balls. For example, what we can specify is the K1 balls inside box 1, K2 balls inside box 2, and the K, let's see, I have N ball. Maybe sorry, it's best to use the N here. N balls in the K box. Maybe it's better to use. So this one to be K10, okay, K2. All right. So here will be N1 balls inside here, N2 balls here, NK balls. All right. So the summation equals okay, will equal N. Total number is N balls. All right. So we want N1 ball inside box 1, N2 ball inside box 2, and N3 ball, NK ball inside box K. So that's case box. All right. So let me give you a situation. If I want to see, I want to talk about these two. Okay. We have one situation is so I have to stress here, we're considering situation, balls are different. So these balls are different. We're considering situation. All right. So we want to put n balls into K boxes. Where box I contain ni balls. So what's the total number of different arrangements of this? All right. I don't have space. Okay, so let's consider. Maybe let's consider this particular example. So here maybe two, one. Let's use this real number. So this one ball, this one two balls, this one. All right. So how can we put these? We want to put these 4 balls into these 3 boxes. And I want to know the total number of different ways for putting these 4 balls into these 3 boxes. How do we do it? All right. So what we can do, just starting maybe from the first box, is allow 1 ball. The balls are different. So what determines is where we choose this ball. The number of ways to put 1 ball inside the box is we choose. So here there are 4 balls. Choose 4, choose 1. So we choose 1 ball, put it inside. All right. So there's a number of different ways for this one. Now have a number of different ways for second box. Once we have put 1 ball here, for example, here I may just put ball B inside. So what's a number of different ways to put 2 balls inside box 2? Provided that one ball is chosen already. So B is chosen already. Of course, we need two balls from the remaining balls. So that will be C. Choose. There are now three balls. Choose two. Okay. So then for this one, only one ball left. So we can choose from remaining balls. So will be here will be 1, 1. So that gives us the number for this problem. So in general, what does this one give us? In general, what does this one give us? So for first box, let's write in this one. So we choose K as our N1. N1 balls. That's for first box. Now for second box, number of balls left is N minus N1. So here is N2. And if we continue, here is N minus N1 minus N2. Here is N minus 3, and so on. Eventually, so here is Nk. No one is Nk. It's so the previous one will be N minus Nk, sum of everything. The sum of N1 plus Nk. So which is Nk, okay. So eventually by product rule, multiplication rule or product rule, it will give us this formula. So this one looks complicated, but actually it is not. I'm not going to give all the details. It's quite very simple because it cancels. A lot of things cancel. Eventually, once we get, so this one, a lot of things will cancel. It's very easy, simple exercise. I will leave it to you. Okay. Eventually, what happens is n factorial here divided by n1 factorial, n2 factorial, up to nk factorial. That's the number. But in this case, we know how to do it. It's quite simple. So we just use this formula. But let me give you two examples for the first case. Okay. I really want to clear this one up so I have enough space. Right. Okay. So this formula, remember? So remember this formula. It's very simple. Okay. I'll have to do this one. I will we'll do it in a minute. Okay. So let's see. Say everyone played poker before, right? So let's consider the problem. I distribute five cards each to 4 players. Okay, so we have a deck of 50 cards. Forget the control. So we have so for 52 cards, so there are 4 present. Okay, so it's a round. We want to distribute 5 cards to each of them. We want to know the total number of different ways to do this. All right. Now, this case is easier formulated as this model, all box model. All are 52 cards. These are balls. And the boxes. So each person, different person, of course, are different. So we have 4 different boxes here. So we have 1 box here, 1 box here, 1 box here, 1 box here. All right, so problem can be modeled by all and box models. So these are different boxes. All right, so 50 cards, we have 4 boxes. One settle thing here. Okay, actually, it's not 4 boxes. It should be 5 boxes. There another box with 32 cards. These are the remaining cards. Okay. So when we deal with it, distribute the card to 4 players. So these are 4 boxes, but there are remaining 32 cards. So problem actually distributes 52 balls into 5 boxes, not 4 boxes. They're remaining cards. All right. And so what happens is just we can now use the formula. It's very simple. 52 factorial divided by 5 factorial. There are 4 of them, and 32 factorial. This is the answer. I don't want to compute this number. I don't know how large it is. It should be very large. So that gives us different ways to distribute 5 cards to each of our players. So you can see it should be a large number, right? So that's one example. Next example is this one, and then we relate this one to the ball box model. Actually, this is where the name comes from, permutation with repetition. All right. Now let's consider this problem. Okay, so right, I give you 2 zeros and 3 ones. How many data streams can we construct from these 5 symbols? So of course, this one will be one of them. But there are others, such as this one, or this one, right? There are many. How can we determine number of different bit streams that can be obtained from this one? So what we are doing, actually we are doing commutation. Let me explain to you the situation. So suppose these are 5 different numbers. So instead of this, I give you 0, 0, 1, 1, but 0, 0. Suppose they're different. So I just add a subscript to them. So 1, 2, here. One page different, 2, 1. All right. Now what's the different number of strings can be obtained by these 5 characters? So then it's quite obvious. It's a biofactorial. Because we are really dealing with the permutation of this one, right? So now the difference is in the permutation, these two are the same. So in terms of permutation, if they're different, I can have 0, 1, 0, 2, say 1, 1, 1. Okay, 1, 2, 3. 0, 2, 0, 1, 1, 2. So these two are different when these are different. And now if this 0, 1, 0 are same, then these two will be regarded as same string. So that's a difficult. If we just use permutation, they will be overcounted. So we need to avoid overcounting. So when they're same, these two should be regarded as same string. All right. So here, the problem can be viewed as a permutation of this one using 2 different types of objects. So here are different types of objects. The first type, N1, first type, type 1, type 1. And N2, type 2. So we want to do a permutation with N1 of type 1 and N2 of type 2. So how can we do it? So that fishing allowed is in terms of type of elements, I only give you two types, 0 and 1. So N1 objects of type 0, N2 objects of type 1. I want to give a permutation of length N using different types. So that's where the name comes from, the permutation with repetition. We want to permute N1 objects of type 1, N2 objects of type 2. So there are many objects at the same time. That's the repetition. Now, actually, this problem can be modeled as ball box model. One way model it in this way is obvious. So what happens in text? What text corresponding to boxes? The corresponding to boxes. So here I actually give you two boxes. One is 0, one is 1. All right. Now I have you 5 positions. Computation that's length in 5 positions. The position corresponding to balls. Computation say 0, 1, 0, say 1, 1. This commutation corresponding to the following. The first and third positions, these two positions go to box 0. And the other 3 positions, 2, 4, 5, go to position 1. So this problem can be really modeled by this model, all box model. Positions of balls, types are boxes. All right. Now the problem is to put n positions into these boxes so that each box I has ni positions. So we know how to do it. So in this case, there are 5 positions, 5 balls of 2 types. 2 zeros, the 2 vectorial, here 3 ones, 3. That's it. Okay. So there are such correspondence between permutation repetition and this ball box model. All right. I see a question maybe. Let me see. Also, it's just a solution. No, that's not 2 to 5 because of repetition. Okay, not 2 to 4. Okay, so the answer should be this way. Okay. So that's first situation when we deal with distinct boxes, distinct balls. Balls are different. All right. Now consider second condition, a second situation. Now we consider the situation that balls are same. This is still different. The balls cannot be distinct. But here we have all identical balls. All right, I want to put n identical balls into k different boxes. So that's the situation. Put n. I want to know the number of different ways. So here I want to put 4 boxes, sorry, 4 balls into 3 boxes. So for example, we can just do it with hand to see how many different situations can we get, for example. So let's do a couple of them maybe. To get a feeling first. That's 1, 2. All right. So I don't care about how many balls inside each box. I just want to do different ways. So for example, I can put 1 ball here, 2 balls here, and 1 ball here. That's one solution. Or I can put a no ball here and 3 balls here and 1 ball here. Or one ball here, 2 balls here, and 1 ball here. So here I have 3 different solutions. All right. Okay. So that's a model. Now, this one related to combination with repetition. Okay. So what it means is we choose an object from a of objects. All right, so that's what we mean by combination with repetition. We choose an object from k types of objects. So we have k types. So type 1, type 2, and type 3. So here type 1, type 2, and type 3. So we can choose as many as you can choose as many as you want from each type. So each type has unlimited supply of objects. Actually, at most n, so n will be sufficient. No need to be infinite. So assume you can choose. We can choose so maybe 2 here, 1 here, and 2 here, for example. Yeah, so that's the model. So these were really equivalent because this problem can be modeled in this way when regarding each type as a box. Again, each type is a box. Each type is a box. We choose an object. So when we do this one, typically we look in this way. We put it inside. We put all here. If we look in this way, it's better to look the other way around. We choose a ball from the box. So it's more like this direction. But the same thing, right? You put this ball inside or you take this ball out. They are really the same thing. So this one can be really modeled by this model when each box represents a type. All right. Now we want to choose an object from these k types. For example, the first example, we choose 10 pieces of fruits from 3 types of fruits: apple, orange, banana. I have 3 baskets. So instead of drawing in this way. Okay. I have 3 baskets of fruits. So here I have apple, here's orange, and here's banana. Now I want you to choose 3 fruits from these baskets. Each basket of course, here assumption is each basket contains at least 10 different fruits, 10 pieces, 10 fruits for each type. Otherwise, it's more complicated. Okay. It can be partly the same idea, but you have to consider a few cases. So these 3 types will be boxes. I want to form, so here are the 10 balls. Here 10 of them. From this problem, 10 of them. I want to form these 10, I choose 10 balls from these 3 boxes. I choose 10 pieces of fruit from these 3 baskets. I want to know the different different ways to choose such 10 objects here. So there's a correspondence between this model and this model. They're very same problem. All right. So I'll give you a general formula, and it's easier to describe using this model, analyze it using this model. Once you see it, this one and this one, the same thing. All right. I see another question. Let me see. Okay, I answer you later. Okay, it's easy. I don't, because you're asking a question about a previous one. Let me finish this one first. Okay, I'll answer you later. All right. So now, how can we solve this problem? It's easier to consider this model. Okay, let's see. All right. So let's, in order to solve this problem, give a formula for this one. It's better we can put these boxes. So there is these boxes here. Put them side by side. All right. Okay. Now these balls will be put inside. So let's see. So for convenience, perhaps we could line it. So that's one possible solution. Say, let's say seven, let's say, I mean, 7 balls. So here are 4 boxes. All right, so this is 7 balls, 4 boxes. First thing to observe, what matters is the number of balls inside each box. Because these are same balls. So what really matters is the number of balls inside same box. All right. So that's what give us 1 ball here, 3 balls here, 2 balls, 1 ball. Now, if I draw it, another, so how can I use this type of representation to tell how many balls in each box? So that's another one. So if I draw this one, you can immediately see what I mean by this configuration. Now, another thing to notice is reality and the past, these two are not really necessary. Without this one, I can still tell they're different. If I can exactly tell what it means, right? So this one means 2 balls in box 1, no ball in box 2, 2 balls in box 3, and 3 balls in box 4. Of course, this one ball in box 1, 3 balls, 2 balls, and 1 ball in box 2, 3. All right. So now, so let me go a little bit longer for this middle box. But even can regard this as 1. All right. So what happens? Really, we are looking for a string. So we're really looking for a string. If regarding each ball is 0, each bar is 1. The problem is really looking for a string with k zeros, with n zeros and k ones. To see how many strings we can form on this one. All right. Now this string, how do we form this string? Really depends on the position of these 8 balls. Where put together how many positions? Total number of positions is n of k minus 1 positions. So really you can think we have these ones there. I want to insert zeros. I choose position for zeros. In this many position, I choose how many zeros, n zeros. maybe K is, let's see, K box, and maybe there are other, typically in one byte, maybe K is smaller than N. So maybe instead of this one, say K, I choose bars instead of choose these separators, choose ones. So we choose K ones. K position for ones. So problem is really from N plus K minus 1 position. We choose K position for ones. Once we have chosen this K position for one, we know how this box is divided into K boxes. So you can think this is a large box. Then you need one to divide it into K boxes. So once we know these positions, then we know how they're divided. All right. So a number of different ways really is to choose N plus K minus 1 objects. From this many objects, we choose K positions. So that gives us N plus K minus 1 here is K. Or that's the same as N plus K minus 1, N minus 1. Oh, one here K minus 1 position, sorry. It's K minus 1 position, sorry. Number one is K minus 1, it's not K. Okay. The K boxes. Separated number of R to separate them is K minus 1. Okay, so here it could be K minus 1. Or in this notation, is C and K minus 1. Usually it's easier to compute with K. Typically, this one is smaller. Typically, we use this one instead of this one. These are equivalent, but typically we use this one. Okay, let's give a general formula. Now for this problem, let's see how it works. All right, so let's see a number of different ways to obtain 10 fruits from these three types of fruits: apple, orange, and banana. So in this case, n equals 10. So these are balls. And number of boxes, 3. K equals 3. 3 types. So apple, orange, banana each is regarded as a box, right? So the number of different ways is 10 plus 3 minus 1, choose 2. $11, choose 2. Okay, that give us 55. Let me check. Yeah, nowadays don't compute these things carefully. Okay, it's 12, yeah. Okay, yeah, and that's going to be 12, sorry, yeah. 12, okay, 12, 11, 66, so 66 different ways. Okay. All right, let's see. One question. Oh, yeah, K minus 1, yeah, thank you, yeah. I correct that already, okay. Thank you, yeah, for noticing it. All right, okay. So that's a solution for this one. Now consider the last one. Like, give me an equation. So here I have equation x1 plus x2 plus x3 equals 10. Right? I want to know number of different solutions consists of positive integers. The solutions are positive integers. All right. So for example, I have a solution, say 1, 5. There's a solution. There's another one, 2, 7, 1. So these are solutions. Okay, so there's a problem. Now, do you see the connection between these two problems? Actually, they're exactly the same problem. So these are different names, X1, X2, X3. I can regard them as boxes labeled by these three things. I can regard X1 is a label, so corresponding to apple, X2 to orange, maybe X3 to banana. So 10, I want to choose 10 pieces. All right. So in that case, I have, again, it's 10 balls, 3 boxes. The solution will be exactly the same. So these are just the label of the box. Apple, orange, banana, they're kind of the box. One label. A label. L-E-L, so then I forgot. Okay. So these are really the same. All right. Now this makes things a little bit complicated. We're still looking for positive integers. I'm sorry, still looking for solution of positive integers. Give you some constraint on some of the x, some of the variable. So I want xi to be at least 2, maybe x2 at least 1. So I want still looking for different number of positive solutions under this constraint. So what happens is, again, I define this one as boxes, x1, x2, x3. So what this constraint means, I already put the 2 balls inside box 1 and 1 ball inside here. The total available number will be reduced. So it becomes x1 plus x, maybe y1 instead of x2. Equals 7. The solution will be positive integer solution for this one. The solution with this constraint is the same as solution for this one. Okay. So it's now n becomes 7 instead of 10. So it will be 7 plus 3 minus 1. Here it's still k minus 1 is 2. So it's 9 to 2. That's 36. Right? Yeah, 36. So number of solution will be 36. You can also put upper bound and so on. All right. I think that's the I think we can only come to this steps. I have to remind you, it can be very subtle. Sometimes it's not easy to tell what is box, what is balls. Just adding pigeonhole things about sometimes not easy to tell where to find the boxes and balls. So this is also the same situation. But basically, we have only 2 situations. One is permutation with repetition. One is a combination with repetition. So in some ball box model is boxes are different. So you only need to remember, as far as this cost is concerned, our boxes will always be different. Otherwise, it's too difficult. So that's what's required for this cost. You only need to remember that all boxes are different. Then balls will be either same or different. If they're same, we have this combination. If they're different, we need to deal with permutation. All right. Okay. I think that's it for today. And starting next week, we only have 3 more weeks, I think. So I will start with the binary relation next week, then graph theory, because these are extremely important. Actually, they're sitting in the heart of discrete math, relation, connections. Unfortunately, I don't think I have any time to discrete probability. My understanding is you are taking calls on the probability, so they're dealing with continuous seeds. The basic ideas are there already. So to discuss probability in depth, I think at least 1 or 2 weeks. So otherwise, not much point. Just give a basic concept. I think you know already, right? Okay. So starting next week, we'll discuss binary relations. All right. So see you next week. I hope that your midterm marks will be available. Will be definitely available by next Wednesday, perhaps even earlier. All right. So far, it looks not bad. Actually, it looks quite good. I did a random sampling, as I indicated in the home page. It's about very close to 70%. Of course, final result I don't know. Okay, but I do expect between 60 and 70, maybe high end of 60. Okay, so see you next week. Right. Homework 3 is due today, right? Okay, and tomorrow in the tutorial, tutor will discuss the solution. All right, so thank you. Bye bye.
Oh, hard to.
Oh, you mean sum is less than n? Yes, then some ball cannot be put inside. Is that what you mean? Okay. Do you hear me? Do you hear me? Hello? Can you hear me? Yeah, I asked you to unmute. I asked you to unmute. You did not do it.
Yeah, sorry, because I was just typing.
Oh,
And
okay. Okay. Yeah, I don't quite understand what you
and
mean.
I mean that if you have a total of n balls, like, and you have k bosses, each boss has each boss can contain at most
That's actually
ni.
it's not capacity, it's a requirement. You need to put the NI balls into that box. It's a you can say it's a requirement. It's not really capacity.
How about at most? If the question is at most.
It's still same. Or if you or you're thinking at most,
Yeah, yes.
or at most you then it's different. Uh, then it's more complicated. You have to consider cases, I think.
And the capacity sum may not be equal to the number of
Yeah,
balls.
okay. If you need at most, then you have to consider cases. I don't think there are easy formula. Of course, you can write a summation, but I don't think you can get an easy formula.
Oh, okay.
But yeah, you need at most, right? Yeah.
Yeah.
Otherwise, I get confused. Yeah. Yeah, that makes sense. Yeah. I think about it to see if there are easy ways. I doubt it will be summation, and that can be quite messy.
Okay. Thank
Okay.
you.
Okay. Thank you. Yeah.
So there's no easy formula.
I guess not.
So the formula can only applies if the if.
Equal exactly that number.
Okay, thank you.
Because if you think about the permutation with addition, if I give you two ones, like what you mean I can throw one away, some zero away. The string is shorter than n. The string is shorter than n. The eventual will be summation from 1 to n, maybe, or from some number to n. You put a less means actually you do not use certain type less than k times, less than sorry ni times. Okay. 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 Bye. If you have further questions, send an email. Okay.